Hi guys, in this video today we're going to be talking about something called linearizing. Linearizing is an interesting concept. What it does is what we use it for is we use it to change our graph to see relationships between variables a little bit easier. Because for instance, let me take a look at our AP sheet for a second here. Okay, I've just highlighted a couple of formulas here, but I highlighted a couple of them because I want to talk about relationships. So for instance, let's look at this kinetic energy equation. We know that kinetic energy is proportional to mass. And we write that, we say kinetic energy, and then we use this symbol that looks like this, should probably be a little bit taller, is proportional to mass. So kinetic energy is proportional to mass. What that means is if I double the mass, I'm going to double the kinetic energy. Look at the equation. If I double that mass, I'm going to double the kinetic energy. But not all relationships are proportional, exactly proportional like that. For instance, the velocity, if I double the velocity, well, then what happens? If I double the velocity, I actually quadruple the kinetic energy, right? Because if I double this and I square it, and that takes 4 times. Similar here, this is centripetal acceleration. And if I double the radius, that's going to cut the centripetal acceleration in half. Whereas if I double the velocity, that's going to quadruple the centripetal acceleration. And it even come down here, we have a square root equation. This is one that we've been working on recently. If I double the length, I actually take the time of the period of the pendulum, and I multiply it by radical 2. If I double gravity, maybe take it to a different planet, then I actually take that period and divide by radical 2. So each of these equations that I've highlighted have relationships, but they're not always direct relationships. The advantage to direct relationships is that if we graphed them, we could see that there is a linear relationship. So if I graphed this, where kinetic energy was here and mass was here, I could see a straight line as a relationship. Whereas if I plotted kinetic energy against velocity, that's not going to be a straight line because it's a v squared, so it's going to have some sort of a curve to it. We're not sure exactly what it is. So that's what we're going to talk about today, is how to make it a straight line. Because if it's not a straight line, it's just not as easy for us to see the relationship. And then what we'll do is we'll take that straight line and we'll make it fit the equation that we're dealing with. Okay, let's take a look back at our worksheet again. Okay, so a couple things at the top here. Not all relationships we study in this class are directly proportional to one another. That's what we just talked about. To solve graphically for constants, scientists often linearize data. This does not mean drawing a linear best fit line through data that is not linear. It means changing what we graph so that we do have a linear function. Okay, let me tell you what that sentence means. What that sentence means is, what it doesn't mean is we don't take something that's not linear and just draw a straight line and say, actually, it's like this. That's not what it means. What it means is we have to actually manipulate our variables so that we actually get a straight line rather than a curved line. And the reason this is coming up now is because that lab that we did at the very beginning with the pendulum, and you did a smaller pendulum on the computer simulation, and then we did that longer pendulum that I did on that video, and we started to see that the relationship was a square root relationship, right? And the only reason we could see that is because we had enough data. If we had stopped here, it would have looked linear, right? But then it rounds off. And so that's when we realized it's not linear, it's actually square root. That's why we're talking about this now, is we have a good set of data from that pendulum lab that we can use. Okay, so let's look at some of the things that we could possibly plot against each other. Maybe we have 2 variables, and when we plot them, we get a straight line. That shows us there is no relationship between those variables. That is, x is not affecting y. What do we have to do to linearize it? Nothing, because it's already a straight line. And what would that expression be? Y equals k. Like whatever this k is, this constant, and it could be like a spring constant. It could be, there's a variety of constants that we've worked with, but that would just mean that is our spring or our k, our constant. All right, sometimes though, we do get a linear relationship with a slope to it. And so in this case, as x increases, y increases. In this case, as x increases, y decreases. That means that y is proportional to x. So we would say y is proportional to x. And then this one would also still be y is proportional to x. It's just in a negative, it's a negative relationship. Okay, what do we have to do to linearize it? Nothing. It's already a straight line, so we're good. So this just means that we're going to have y equals mx plus b or y equals negative mx plus b. Okay, what if it has a shape like this? You have to go back to your math classes and you have to remember what some of these things come from, what the parent function would be for some of these things. And so this could be a 1 over x function. So this is like a minute ago we were talking about centripetal acceleration, and centripetal acceleration is proportional to 1 over r. So we could say centripetal acceleration is proportional to 1 over r. Okay, and so this, if we graphed this, we would get a rational graph. That is, we would get something that looks a little bit like this. So again, what this says is it says that y is proportional to 1 over x. Now, like I said a minute ago, that is not something that is easy for us visually to see how they are related. But what we can do is we can change our graph. And instead of graphing it y and compared to 1 over x, we could change it. And this would still be our y. And what we could do over here is make this 1 over x. And so we would have to change our data. We'd have to do another column in our data to find out what that is. And when we did it, it should then make a straight line. And so that's what we're going to be working with. And then what we would do is we would look at this equation and how to make this equation fit for our data. And we'll look at examples of these so you can see how it's happening. All right, this one, I don't know if you can tell, but this is actually a half of a parabola, right? And so in this case, y is proportional to x. So what do? We're going to change our graph and graph it y compared to x squared. So we're going to take that data and we're going to change the data so that when we graph it, the new data is going to make a straight line. And again, we go back and look how this is really the y equals mx plus b equation. We are just changing that to x squared because that's what we have on our x spot now, okay? And again, we'll look at some examples. Okay, I don't know if you can tell, but this is like a square root function a little bit, right? And so here we have y squared is proportional to x. And so what we need to do is we need to change our graph to make this the y squared and this the x. And now this is the first time that we've actually changed our y. On all these others, we changed our x-axis. We changed our x-axis here, we changed our x-axis here, but what we're saying is maybe instead of changing the x-axis, maybe we need to change the y-axis. And so again, we get this as our equation to start with, but it's a y squared equation, and then it'll give us the relationship that we are looking for. Okay, on the back of this paper, I have some examples. So we are going to go through and do a couple of these together, and then I'll leave a few of them for you to do on your own. Okay, let's read through the instructions. This is how we do linearization in physics. A lot of you, I think, have done linearization before, maybe in calculus class, maybe even in statistics class. So what we're going to do is we are looking for the mathematical, it says expression. We really want the relationship. It's really what we're looking for. So we're going to come up with the expression or the equation to give us that relationship. To do this, first graph the original data. Assume the first column in each set of values with the independent, the second column is the dependent. Then, taking clues from the shape of the graph, modify the data so that the modified data will plot as a straight line. Using the slope and the y-intercept from that, write an appropriate mathematical expression for the relationship. Okay, and be sure to include units. Here's the deal is, in math, we use y equals mx plus b, but in science, we're going to use the units that they are giving to us. Okay, but what this said up here, assume the first column to be the independent and the second column to be the dependent. So we are going to put the volume, or the V, measured in meters cubed, on the x-axis, and we're going to put the pressure measured in pascals on the y-axis. And we're going to plot our original data. Just so you know, these graphs, I know they're kind of small. The major grid lines there are 10 of them. And so if this is going up to 10, I can just count 1, 2, 3, and so forth up to 10. And going this way, again, there are 10, so I'm going to go up to 40 up here because of this, and so I'm going to count by 4s. Give me a second here to fill in those hash marks. Okay, now that I've filled in my axes as best as I can, I'm now going to start graphing. And notice how these are getting really kind of small, and these are kind of small. So you might, I don't know, you might not always start with the first one. You might start the other way, or you maybe start in the middle, something like that. But these little tiny decimals might be hard to do. These aren't too bad. We can probably do this, 0.140, 0.58, etc. Take a minute now to plot those points. Okay, my graph isn't beautiful, but here we are. If you look at this, and let's turn over to the other side of the worksheet for just a second, because we're going to look at which one that would this most easily fit with. And so if I look through here, it looks to me, it looks a little bit like this one, right? These three, this one, it's not curved that way, it's not curved that way, it is curved this way. So this is a 1 over, and it's 1 over x. So let's go back to the other side. If that is 1 over x, remember this is my x column, what I need to do is I need to make another column and call this column 1 over v. And there are a couple ways you can do it. You can just do it, one by one, like in your calculator, just each problem. I'm going to show you on your graphing calculator a way that might save you some time. All right, I don't know how often you've done this, but we did this in Algebra 2, where we're going to enter our table into our calculator. So we're going to do a couple things with that, but the first thing that I really want to do is take this v and make it into 1 over v. So like I said, you could just do it one by one. That's fine. That is not a problem. But I want to show you on your calculator. If you go to Stat, Edit, and I have some old data in here, so I want to clear out that data. To clear it out, I go up to the L1 and I hit Clear, and then I arrow down, and then I go over to L2 and I go up, and I hit Clear, and I go down. So now I've got empty tables. Okay, what I want to do is I'm going to put the information from the volume, the V column, into L1. Okay, so I put all the information from the V column into L1 in my calculator. Now what I'm going to do is I can arrow up to the L2. And notice down here it says L2 equals. I can start typing in, and I can say, well, I want it to be 1 over v. And you guys know, right, that 1 over v is the same as v to the negative 1. And so I could do two things. You know what, I might just do 1 over v, but you could do v to the negative 1. Okay, let me go back. I'm here at the L2. I'm up on the L2. I'm not in the column. I'm up at the heading at the top. It says here L2 equals. I need to click back onto my calculator because it is, okay, now I'm here. I'm going to click up here. I say L2 equals, I can type in 1 over L2. And to get, L1. And to get to L1, you go to second, L1, enter. And it just gave me all the numbers that would be 1 over that. So in other words, I can now write these numbers over here on my new column in my table. Now, those were probably easy enough that you could have done mentally, but I wanted to show you on your calculator so that when they're not as easy, you're able to do that. Okay, now what we do is we are going to make a new graph. For this case, the Y column is still pressure measured in pascals, but the other column is now, instead of V, it is 1 over V, and that would be measured in 1 over m to the third. Okay, that's 1 over volume. And so my hash marks for my y-axis, the P, are still going to be the same. I'm going to count by 4s. I'm going to do that on my y-axis. On my x-axis, you know what? I'm actually going to keep it the way it was because I have to go up to 10, and it's still at 10. It's just kind of backwards, but it's still the same. So I'm going to go back and repeat my hash marks on both sides. Okay, now I'm going to have my axes set up. Now I'm ready to go ahead and start plotting the data. So again, take a second now to plot that information. All right, I just got the first 4 of them plotted, and I'm going to have to start really filling in there tiny. But you know what? I think I have enough, don't you, to already make a decision about this. I'm going to go ahead and draw my line. Okay, so I went ahead and took my straight edge and drew that in there. And let me just mention straight edges. If there is any graphing on the AP test, you ought to use a straight edge. So a couple things you need to have with you when you take that AP test. you need to have your equation sheet, you need to have your calculator, and you need to have a straight edge, because if you have to draw a line, it needs to be a straight line. Okay, so we're going to start with a y equals mx plus b. Our m is our slope, and we do rise over run. Do not do just counting boxes. Do it by what's on your axes, because the rise here is 40 and the run is 10, right? Because we go up to 40 and we go over to 10, and that reduces down to 4. And so now what we have is we have y equals 4x plus, and it is 0. Most things in science will have a 0, 0. Okay, that's most things will have a y-intercept of 0. Now we have one more step, and that is this is not a y and an x, right? We're in science class. This is math stuff. We need to go back to science. My y-axis is my P, my pressure, and my x-axis is, in this case, it's 1 over V, right? It's not V anymore. It's 1 over V. And so we could say that pressure is 4 over V. And so that is our linearized equation. All right, let's do maybe one more example of that. Okay, let's do the bottom one together, and then I'm going to have you do the middle one for your own homework, okay? All right, so on my y-axis, I need to get all the way up to 80, so I'm going to count by 8s on these increments. So count by 8s all the way up to 80. On my x-axis, the time, I need to get up to 20, basically. I'm going to just kind of round that up to 20. So I'm going to count by 2s going this way. All right, so now I have my axes set up. Now I'm going to go ahead and start plotting my points. This is one of those that I was talking about where, you know what, I might start at the bottom here. Like those decimals, I just don't want to deal with those right now. So I'm going to start down here to start getting a little bit of a pattern before I have to deal with these tiny little numbers. So I'm going to go to 19.280, which is awfully close. Well, actually, I have a line for 19, so that's good. So I'm going to start plotting there at that point. I'm going to work my way down. Okay, here's what my points look like. And again, this is not perfect. We're doing this by hand. You could do this in your calculator. And I'm going to show you real quick and remind you how to do that. You could put this in your calculator. The way you do it, and I have some different data in here, in mine right now, but the way you do it is you would go to Stat, Edit, and then you would put in your data. This is the data for the next step that I have in here, so we can talk about that in just a second. But here I have all my X points. What I did here we'll talk about later. But that's how you put that in, and then to go to the correct zoom level, you go to Zoom Stat, which is 9, and then that'll plot your points. And again, I have different data, so mine's different, but that's how you would do it. But for now, since we did it on paper pencil, let's go ahead and use our pencil and draw that line in there as best as we can. Okay, remember I said most of science will get to the point 0, 0. So typically we want to go down to that 0, 0 point. And so we have this curve. And so now again, we have to think about which one we should use. If you're not sure which one this looks like, let's go back to the other side for just a second. So once again, we're kind of looking at these 3 curves. And I would say that this curve is it, right? Now, in math, we would say that this is a square root curve, right? And I think when we did that pendulum lab, I even called it a square root. But in this case, instead of square rooting, we're going to go ahead and square the y value. And that's what we're going to do next. So in other words, this time, and I've kind of run out of space here, but this time what I want to do is I want to squeeze in another column here, and I want to call this column v squared. And so I'm going to square each of these, which we can do in our head. That's pretty easy. Fill those in real quick. Okay, so that's what I have here. And that was, like I said a second ago, that was the information I had on my calculator. So here it is in my calculator. Those are the values you should have in your third column, the one that you've added on to the side for the y values. And so now when we graph this, our graph is going to look quite different because our velocity, let's see, our time did not change at all. So our time is still going to be over here. It's still going to go up to 20, and we are measuring in seconds. However, my velocity is now not velocity, it's v squared, and those units would be m squared per s squared. And so I need to go all the way up to 6,400. How am I going to do that? Well, I'm going to have to make it fit. So I'm going to have to count in here and see how to make that fit. All right, you know what I'm going to do? I'm going to cheat a little bit, and I'm going to count up to, count by thousands, 1,000 all the way up to 5,000, and then make another one for 6,000, and then make another one for 6,500. That's what I'm going to do on my y column. So again, this is v squared meters squared per second squared. But then on my t, I'm just going to get up to 20. And now I need to plot and see how this plots out. Right, so when I plot my points, this is kind of what it looks like. I'm going to get a straight edge, and I'm going to connect these with a straight edge. Okay, so my graph is going to look something like this. Now, remember the last step is to go back and figure out what is the equation of that line, and so therefore what is the relationship. Okay, we're going to start with y equals mx plus b. We're going to find our slope. We are not going to count boxes. We're going to use the numbers. The numbers, it went up to 6,400 and over 19.2. And so if I take 6,400 divided by 19.2, I get 333.3 repeating. Okay, so we get y equals 333.33x, but of course it's not y and x. Our y is v squared, and our x is t. And I probably should go ahead and include those 0.33, so let me erase that. And so this is my linearized version of the equation. I'm going to go back where I said I had that in my calculator, and I'm going to just double check a couple things and make sure that comes out the same in the calculator. Okay, so here's my graph. Remember to find the equation of that line. What you do is you go to Stat, Calc, and then you go to Linear, which is the fourth one down. And L1 and L2 is good. We're going to store it in vars, yvars, and we're just going to hit enter a couple times. And here's the equation that it gives me. Notice it's 328.9. We had 333.3. That is awfully close, right? And the B we had as a 0, they had as an 8.5. But looking at our data, to get, the difference between 0 and 8.5 when you're measuring up to 1,000, that's a pretty tiny little difference. So I'm okay with what we have, even though it doesn't exactly match the graph or the calculator. I think what we have is pretty good. I think either way you did it, if you were taking a test and you wanted to do this on your calculator, that would be fine. You want to do it by pencil and paper, that's okay too. So your job now is to go back to the middle one. And can you plot these, come up with what they are, come up with the equation. When I was editing the video, I noticed that I had a mistake. So I had 4,700 here. I'm going to change this to 4,900 and see if that changes the equation. Okay, so I changed it to 4,900. I went to Stat, Calc, Linear Regression. I'm going to go down to Store the Equation, vars, yvars. And look at this. Now I have that same equation that we had with pencil paper. It was 333.33. The b, the y-intercept is 0. So it was just a typo on my end.